are a country that doesn't have any source of development.
No.
Because you told me before there is camel in your country. Yes, I have a camel, but not the states. And if I give you babies about Egypt,
My country is not developed that.
What developed?
Undeveloped.
Undeveloped?
Yeah.
How did you get this idea?
Huh?
How did you get this idea?
Because the country is very huge. And, there's a lot of, how can I say?
Not why you told me before you have camels in your country. Why is this question?
Just kidding here.
Okay.
I have trained a lot to speak as fast as you. Yeah. I will show you how can I speak more fast than you.
Nobody can.
You?
When I listen to the lecture recording, I don't understand myself.
Let's do tomorrow.
When I listen to the lecture
You are
recording,
not
I don't understand myself. I have to slow down so understand.
Alia, can I just would like to come to Egypt?
Please come.
I will visit you.
Please do.
But
Do you live in Cairo?
only, but
Do you live in Cairo?
No, I should visit anything except Cairo.
Yes,
Cairo is very
Aswan.
Where do you live?
In Cairo.
In Cairo.
But Egypt is not Cairo. Egypt has more tourism.
I will visit you and you'll be in your home.
Please do.
Yeah.
My mother know you.
Are your mother?
Know you very
Yeah.
well. Like I keep telling her
She'll be my friend. She'll be my friend.
Sure, please do.
Eh?
Please do.
And she speaks very fast as you.
She speaks fast, yeah.
Yeah.
But not as me.
Nobody speaks fast as you.
Correct.
But you are the president of the
I know. You are the president, she's the boss.
But you say president in a wrong way.
Eh?
You have to say.
I think majority will join via Zoom. The rest can hear in the group.
Yeah, I don't let people because of the weather. And I think people started.
Great morning, everyone on Zoom. We're kind of sparse in the classroom this morning, so we'll probably wait another minute or so here, and then we'll get going.
People will arrive wet. You have more homeworks.
What's that?
Will you have more homework?
No, there's no more homework. There's only 5.
Oh, yeah.
Yeah. So the rest of the class is dedicated to the projects.
Oh,
Okay, it's a couple minutes after, so I think we're gonna go ahead and get started. I do want to do a quick roll call on Zoom because I can't see the full participant list in front of me. So could everybody just chime in briefly on Zoom to say that you're here right now?
Yes.
Yes,
Okay,
I
so
am here.
I see Newman. I
Hello,
see
Professor.
Myra
I'll be here also.
Yes, I
here,
am here.
Sarah,
Thank you.
Newman, Myra, Kier, Sarah, Nancy.
I'm here.
I'm here.
Okay. Okay, so I have Newman, Myra, Kiera, Sarah, Nancy, Na. Who else? I see 10 people, so.
I'm here, Hyunjung.
Hung Jung, okay.
Clara.
Clara. Okay. Anyone else I haven't read so far? Okay.
Emil is here.
Oh, Emil, okay, thank you. All right, that should be the 9. Okay,
So here.
okay. All right, so again, today homework number 5 was due, so Young Chow and I will take a look at those and probably get them back by Friday, possibly Monday, depending on how long it takes to get through them and provide feedback and everything, but we'll get those back as soon as possible. That is, again, the last homework, so there's only 5 homeworks in the class. So the rest of the class is going to be dedicated toward working with your team or working on your final project. So pretty much everything, exercises, everything else from here on out, going to be restricted to making progress and finishing that final project. Okay, so no more homework exercises. But at the same time, as you're working on your final project, if you want to set up a meeting or talk about the project, feel free to set up a team meeting with me at any point. More than happy to chat about any issues that you're having with your project or structure or interpreting analysis results, whatever the case may be. Think of that as being kind of your outside of class assignment right now, is again to make progress, but set up a meeting with me if you need to discuss progress on the final project. Okay, because that's the remainder of the focus here. Now, thinking about deadlines, Monday is the due date for the full draft of the final project. And again, this is a draft. Okay, so this is not a final polished version of what you're doing. Again, this is a chance for me to check in and see how things are going. I've given you feedback on your introduction and your data and methods. I'll look to see that you've incorporated that feedback on the introduction and the data and methods sections. But I'll also give a look at your results and your discussion and make sure that everything looks like it's on the right track there, is consistent with your research objectives, so forth and so on. Okay, so that'll be the focus of the review of the drafts that are due on Monday, is to make sure that you've made good progress with writing up your results, writing up your discussion, so forth. All right. A reminder about working on your results as you're thinking about tables and graphs and things like that. Remember that a required part of the final project is to provide estimates of design effects associated with all of your analyses. So it'd probably be a good idea to revisit the final project description that's up on Canvas and make sure that your team is checking off all the boxes in terms of the requirements for that final project. And one of those requirements is including estimates of design effects for all of the different estimates that you might be reporting in tables, figures, and so forth. Okay, so remember, that's not typically something that would be included in a secondary analysis that you might be trying to publish somewhere or a technical report, but it is a requirement of this class. So including those design effects in your tables and then commenting on them as a part of your results. What are they suggesting about the impact of the complex sample design on estimates of variance for the parameters that you're trying to estimate? Okay, so just reminder that that's a key part of the final project right up here. And I'll give you comments on that depending on what I see in the graphs. So remember, that's due Monday. It's not due Friday. Some people were asking about what was due Friday. There's nothing due Friday. So don't submit your draft on Friday. You have the weekend to keep working on it. Okay, so the final draft is going to be due on Monday. No, sorry, not final draft. The initial draft is going to be due on Monday. I will then give you feedback on those drafts over the course of the week. And then from that point on, you're just responding to that feedback, polishing your final project, doing any additional analyses, whatever the case may be. Another reminder is that in the last week of the course, there are going to be 2 working days. Okay, so in addition to getting feedback on this draft and not having any more homework, 2 of the days of lecture the final week of the course are going to be dedicated to working days. So what that means is that I'll be here in the classroom. I'll also be available by Zoom if people would prefer that, but I'll be here to discuss face-to-face if you have questions about the project, or we can use some of that time to talk about any last-minute analyses, any last-minute write-up that you're working on. So just take advantage of that time as well in the last week of the course. Okay. Okay. Any questions about logistics or kind of the schedule, the immediate schedule coming up here in the next couple of weeks? Any questions? We good? Okay. I see somebody else just joined on Zoom. Who else joined on Zoom? I think one person just joined on Zoom. Could you check in?
What's the question? Sorry.
Somebody just, a new person just joined on Zoom and I didn't see who it was. So I'm
Okay.
curious who just joined.
I know.
Okay, we have a mystery person. Okay, that's all right. If you do decide to check it at some point, please do so. Okay, so today we talked on Monday about multinomial and ordinal logistic regression. Okay, the focus today is going to be on models for counts. So far we've talked about models for continuous outcomes in terms of linear regression, models for binary outcomes in terms of logistic regression. And then we've been talking about models for ordinal and multi-category outcomes so far this week. Now we're going to shift our attention to the case where our outcome variable of interest is a count. Some number of times an event has happened or some number of occurrences or something. That's our primary focus today. And we're going to talk about 2 different kinds of regression models for counts, namely Poisson regression models and negative binomial regression models. So these are 2 different distributions that we might assume for a given count variable. We'll talk about how to fit and interpret these kinds of models today. Okay, so we're going to start with just an overview of count and rate data, which are often collected in surveys. We'll talk about the basics of Poisson regression and go through an example. We'll talk about negative binomial regression, and then we'll go through an example exercise kind of comparing the 2 different approaches to modeling counts and how we might choose between these different kinds of models when thinking about reasonable models for counts. So starting with Poisson regression, many times we're looking at dependent variables in regression models that are actually counts of rare events. For example, the number of times that you've been to visit the doctor in the previous T days, okay, where T is specified as part of the survey question, or the number of times you've been in a car accident in your lifetime, okay, or the number of degrees that you've earned in terms of higher education or something like that. A count of how many times some rare event has occurred over a certain period of time. And we're just calling that in general T as being a reference to the time period. So T, that window of observation or that observation period within which the count is actually measured can vary across individuals. So in these models, one person in the survey might say, oh, well, in the past 6 months, I've been to the doctor 2 times. And another person in the survey might say, well, within the past year, I've been to the doctor 5 times. Okay, so that they're using a different observation window. Sometimes the survey question will ask for that information explicitly, is it as a reminder aid or something like that. Sometimes the survey question will fix that observation period for every single individual. So everybody is asked in the last 4 weeks, how many times has this happened? Or in the last year, how many times has this happened? Sometimes the question fixes T. So in this doctor visit example I'm talking about, that period of time might be the same for everybody. For example, it could be 12 months or something like that. So ultimately, we're interested in the relationship between the actual count Y and some predictor X or set of predictors X that might be of interest. Or we might look at the effect of X on the rate at which the events are occurring. So Y divided by T. So the number of events per unit observation period that we expect to see as a function of the predictors X. Either way, that T observation period figures into our analysis of the counts as what's called an offset variable. So in the context of fitting these Poisson and negative binomial regression models, this is an additional piece of information in the data set that we use to set up the model. And it's sometimes referred to as an offset, but more generally in terms of measurement, it's an observation period across which the number of counts or the count of the events is measured. All right, so this is an additional piece of information. So this is an example of a survey question sequence that might produce this type of count variable. And this is from the 2012 health and retirement study. So these questions were asked to people who are ages 65 and older. So they only applied to that particular subpopulation. So this is another example where if we're analyzing these kinds of questions and they're only asked to a particular subpopulation, we would definitely want to do an unconditional subpopulation analysis because we don't have full control over how many people fall into this particular subpopulation. Okay. So first question is kind of a filter. Have you fallen down at all in the past 2 years? Okay. And you can think about, is that question clear? What does that mean, fallen down? Like tripped outside, slipped on the ice, tripped on your stairs? People might have questions about that. But it's a simple binary question. Have you fallen or not in the past 2 years? Yes or no. And notice that the time period T is fixed for everybody by the question. The question explicitly asks, how many times have you fallen down in the past 2 years? Okay. So if the people say yes to the initial question, I have fallen down the past 2 years, they're then asked the follow-up question that says, how many times have you fallen in the last 2 years? Everybody who says no to the initial question is coded with a count of 0. Okay, they haven't fallen at all in the past 2 years. Everybody who says yes is asked the follow-up question where they can write the number of times that they've fallen. Okay, thinking back to the past 2 years, how many incidents have there been? Or they could say don't know or refuse, which would become some form of missing data. Okay, but in that question, then they write the number of times that they've fallen in the past 2 years. That becomes one variable. That's the count that we're actually interested in looking at. But then there's this other variable that's encoded by the survey question, which is equal to 2 for everybody. Okay, that's that observation period. Everybody is fixed at 2. So from this question sequence, we actually get 2 variables. One is the offset, which is 2 years. One is the number of times that they've fallen, which is our dependent variable Y. Okay? Both of those pieces of information are coded from that question sequence. So this is a look at the distribution of that particular count variable in the 2012 health and retirement study. And this is the typical distribution that you'll tend to see for these kinds of rare events. When you're asking about how many times things have happened, there's a big mass around 0, 1, smaller values of that count variable. And then the distribution kind of trails off with some of these larger values. And you see there are still some counts that are in 20, 30, 40 range. Some people who have experienced falls on a pretty regular basis. Okay, but the majority of the respondents either didn't experience a fall, so there's a lot of zeros in the data, or they experienced a small number of falls, 1, 2, 3, 4, 5, something like that, that they can remember these explicit events. And the idea is, if we're thinking about fitting a model to this type of dependent variable, what would be a reasonable distribution to use when setting up that likelihood? Doesn't look like it's necessarily normally distributed. We probably have a hard time trying to satisfy that assumption of normality in the residuals, looking at a distribution like this. Should we treat it as binary? They either fell or they didn't fall, okay, based on the answers to the first question exclusively. Is that a reasonable approach based on how many people actually fell? Should we actually try to model the count or the rate at which they're falling? And if so, what's an appropriate distribution for what we see here? Okay, so that's kind of the analytic problem when we're thinking about these types of counts. Some counts of more common events, they may look perfectly symmetrically distributed. Okay, if an event happens all the time, right? Like how many times have you taken a shower in the past week or something like that? Some more regular events are going to have a more normal looking distribution, and maybe linear regression would be just fine for those kinds of counts, things that happen all the time. Okay, binomial models, also possible. Poisson and negative binomial, we're really talking about models for relatively rare events. Okay, that's our primary focus, such as falls in the past 2 years. So also I mentioned this is a weighted distribution. So this is giving us a sense of what the population distribution looks like for people who are age 65 and above in terms of how many times you've fallen in the past 2 years. So again, seems like a relatively rare event. All right, here's some additional basic descriptive statistics, okay, on a number of times fallen and then number of times fallen just for the people who have experienced a fall. Okay, so that's the two different types of variables. Okay, so you see the relative sample sizes. Okay, if we focus on everyone, we have about 10,600. You see the median 0, the mean is about 1.2. The standard deviation is 3.3, and the variance is 11. Okay, so one key thing that we're going to think about with the Poisson distribution. The Poisson distribution is defined by having a mean that's equal to the variance. Okay, so if we look at these basic descriptive statistics, does it seem like the Poisson's a good fit here? No, right? There's a lot more variability. There's more dispersion in the data than would be expected, okay, for this particular count variable. And even if we restrict the people who have had at least one fall, okay, and look at that distribution, there the mean is 3.3, but the variance is 23.5. And that's likely being affected by some of those larger reports of people who have fallen frequently over the course of the past 2 years. So when you're thinking about count data and reasonable models for counts, that's a very easy thing to check when thinking about the choice of the distribution. Remember, the Poisson has a conditional mean that's equal to the conditional variance. Here we're just looking overall. We haven't started to adjust for any predictors, but the idea is that when you condition on other predictors, roughly the mean is going to be equal to the variance. And at least in the overall marginal sense, we're not seeing that yet. Now, if there's a variable that might be very predictive of having a lot of falls, maybe that assumption becomes more reasonable. But we're going to see how to check for this and compare the Poisson approach to other competing models as a part of our analysis here. Okay, but this initial descriptive glance at the count data would suggest that we don't have Poisson distributed data where the mean is equal to the variance. Okay? And in both cases, you can see that the maximum number of reported falls is 50. So that might have been a respondent who was like rounding off and saying, well, you know, I've fallen a whole bunch. Yeah, let's call it 50. Right? That might not be an accurate answer, but that's the largest answer that was reported. Okay. Okay. So again, when we're dealing with counts, the question sequence encodes two pieces of information. We have the actual count of events, that's Y, and then you have the exposure time T during which the reported events occur. Okay, so those are two different variables that get coded as a result of this kind of question sequence. And again, the length of that observation period could be fixed for every single survey respondent, for example, the 2 years here, or it may vary from one sample respondent to another. Okay. For example, since you last saw a doctor, okay, how much time has occurred? It might be a question to that effect or something like that. Okay. So the model is flexible enough to allow for a variable observation period, and we just have to be able to know how to specify that to the software, depending on the information that's available. Okay. So regression models for these types of counts, they aim to model the relationship between that response variable Y, which is a count, and the predictor variables of interest, or equivalently, again, the relationship of X with the rate at which the event occurs. If that time period T is constant for everybody, we can really just set T to 1, whatever that observation period might be. It might be 2 years, might be the past week, whatever the case may be. That's where it's not necessarily as of much interest to model the rate. We're just focusing on the count exclusively. But more generally, if T is unequal for different survey respondents, we can accommodate that and model the rate at which the event's occurring. The mistake that we want to avoid when fitting these kinds of models to counts is ignoring T, especially if T is variable for different individuals in the way the data were coded. Because if you're asking one person how many times some event has occurred, and they're using a frame of reference of the past week, and you're asking a different person how many times something has occurred, and they're using as a frame of reference the past year, those counts aren't comparable, right? Because they're thinking about different windows. There were more opportunities for the event to happen if that offset period is larger. So the mistake that we want to avoid when fitting these models is accommodating T that could vary for different individuals. So we have to look carefully at how these counts were measured in the actual survey and make sure we can track down the variables that might incorporate those different observation periods. Okay, that's crucial for these kinds of models. Okay, so one simple approach would be just to calculate that rate for each individual in the data set. Okay, so take the count, divide by the observation period, and just treat that like the dependent variable. Okay, it might be greater than 1, it might be less than 1, but we treat that like a continuous dependent variable and perhaps use a log transformation of that rate and model the log of the rate using a linear regression model. Okay, that's a possible approach that somebody could take, or using some other transformation aside from the natural log. There are two problems with this though, especially with regard to the natural log transformation. We need to figure out how to handle this large mass of zero values in Y. So there's a spike in the distribution that would not be common to any kind of continuous normal distribution or anything like that. That's a property of the measurement that doesn't necessarily fit well with the idea of a continuous bell-shaped normal distribution. There's this big spike at zeros at the lowest possible value. Furthermore, if you look at the variance of the natural log of this kind of rate, that variance is a function of the rate itself. Okay? So what that means is that as the rate is changing for different individuals, so is the variance. Okay, what that means, non-constant variance. Okay, like in the linear regression model, remember, we were assuming constant variance of the residuals. If the actual rate is related to the variance in this way, the higher the rate, the higher the variance by definition. So that's another problem. This is like dealing with the logistic regression modeling problem, right? Remember, where the variance was a function of the observed mean. We don't have the assumption of constant variance satisfied here. So we might need to think about a different distribution, okay, if we're dealing with this kind of analytic problem. A more appropriate approach is to directly model that count variable Y, and a convenient distribution that can be used to model these kinds of counts of rare events that looks like the graph that we just showed in terms of the weighted distribution is the Poisson distribution. Okay, so this is just another type of distribution that we can assume for the dependent variable when setting up the likelihood function. Okay. So this is what the Poisson regression model looks like when you're thinking about using this distribution as a choice. So we assume that that count variable Y marginally is distributed as a Poisson random variable with a rate defined by T times whatever the rate is. Okay, so think about that. The rate itself is a count divided by T. So this basically, the T's cancel out in this calculation, and we're left with the rate variable for that particular Poisson random variable. Okay? But we define that rate as the observation period T times whatever the rate is. Okay, that's what governs that Poisson distribution. That rate variable here is greater than 0 by definition. Okay, so by definition, the rate at which these events are occurring is greater than 0. Okay, for this particular type of Poisson distribution. And what we're actually modeling when we fit these kinds of models is the natural log of that particular rate parameter. Okay, so we're modeling the natural log of the rate as a linear function, a linear combination of the regression parameters and the predictor variables of interest. Okay, so that's the actual model that we're fitting. We're trying to model the natural log of the rate as a function of these different predictor variables of interest. Okay, that's one possible way of specifying this kind of model. But what that gives us is a means of writing down the likelihood. Okay, That's the way that we're relating that rate variable to the regression parameters of interest. So when we write down a likelihood that involves the Poisson density and that rate parameter comes into play, that rate parameter is defined as we have here. Okay? And that allows us to write the likelihood as a function of these regression parameters. Okay? The Poisson density is governed by that rate, and we just replace that rate with this regression equation here, okay, the way that we've written it. That's how we're actually fitting the model. Yeah, question?
With the rate in the previous slide, it equals to y over t, and y can be
Right.
0. So in this case, how can rate greater than 0?
Yeah, so in this case, we're actually modeling it by, or we're multiplying it by the offset. For the Poisson distribution, this is a parameter that governs the distribution itself. So we assume that that can be greater than 0, okay? We're gonna talk about how to handle zeros separately as part of what are called zero inflated models. Okay, we're not quite there yet. We're just introducing the basic Poisson distribution here. But that lambda parameter in the case of this particular model by definition is greater than 0 in this case. So we're going to have a separate approach to handling the zeros in these kinds of models, specifically with regard to rates. But by definition, this lambda parameter in the Poisson distribution is greater than 0. Okay, so we're going to talk about how to model the actual counts that are non-zero in a little bit here.
Okay, thank you.
Okay, so looking at then the expected value of that count variable y, as would be defined by this model, that parameter that governs the overall Poisson distribution, t times lambda, that defines the mean of the Poisson distribution, okay? It also defines the variance, okay? So that multiplication of t times the rate parameter gives us both the mean and the variance of the Poisson distribution. Remember, we set those as being equal. So the expected value of that Poisson distributed variable y is equal to that parameter t times the rate parameter lambda. Okay, so that's our expected value. And if we write down the regression model for that lambda parameter, right, we exponentiate each side of this regression equation here. We're left with lambda on the left side, and then we're left with the exponential of beta 0 plus beta 1 times x on the right side, okay? So if we write that all out here, the mean can be written as the offset variable times the exponential of that regression equation, that linear combination. That gives us the expected value of y conditional on the predictor variables x. And again, that mean for the Poisson distribution is equal to the variance of the Poisson distribution. So the predictor variables, when we condition on them, they determine both the mean and the variance of that Poisson distribution, okay? And as I said, when t is a constant, we can just set it to 1 for everybody. There's no need to account for a differential offset in this particular case. Another way of writing that mean that you see here, we actually add the natural log of t to the regression equation. Okay, this is just another way to rewrite that expression for the mean. So you can see the role that the offset variable plays. It's like a constant term in the regression equation, the natural log of that t, that gets multiplied by a 1. It doesn't have its own regression parameter. It's a constant offset that defines the mean for a given individual, right? So that's why it's so crucial to account for it if it varies across different individuals. And again, if t is just 1 and t is constant for everybody, that term just goes away in the overall equation, okay? Okay, everybody with me so far on the basic setup of the Poisson model, okay? Quick lesson, yeah?
Yeah, I was thinking about if I put before adjusting the model, I translated the output to the same period of time.
Yep.
The time would be more a problem anymore.
Well, so can you say a little bit more about what you mean by translate?
Yeah, because you said that the time is can be different for each answer. Okay?
Right.
Okay. And if I just you answered considering a year, and I answered considering a month, for example. I would transform all data considering the month as the reference.
So you're saying,
Yeah.
you would take whatever count they reported and basically rescale it to the time
Yeah.
period that they were
Yeah,
saying?
before doing the analysis.
That
It would
yeah.
be much different.
Yeah, that would be another possible approach. Like that, it's still the same kind of thing here where you're adding that offset to a given individual. That log of T would basically be the result of that operation.
Yeah.
You're adjusting whatever their count
Yeah.
is for the time period. So I think you'd ultimately arrive at the same results
Okay.
from what we see
Okay.
here. Yeah.
Okay.
Yeah. I mean, that's one possible approach, but again, the danger there is doing that calculation that you said, and then again, treating it like a normal variable. That's not going to be the case, right? Because again, the rate's going to dictate, the rate at which this occurs is going to dictate the mean and the variance. So you could do that, but you would still want to fit the Poisson model,
Okay.
given that distribution,
Yeah.
because of the non-constant variance
Yeah,
problem.
yeah.
Yeah.
I would put the same reference as time.
Yeah.
And adjust the Poisson.
Yeah.
Yeah.
So that's another approach, but it would basically give you the same thing that's happening
Okay.
here, where that natural log of T serves as an offset, right? Right. So oftentimes you see the Poisson distribution just written as a function of the rate parameter. We're explicitly incorporating T here to allow for T to vary across different individuals. Okay, so we're adding that flexibility here and defining both the mean and the variance. Okay, so T, if you assume it to be equal to 1, doesn't figure into the specification. We're just making it explicit here to allow for that possibility that T could vary for different individuals. Okay? Now, what I'm not showing on this slide, you can see it in applied survey data analysis. I'm not showing the density function for the Poisson that's used to write down the likelihood. For practical purposes right now, just recognize that density function, each individual's contribution to the likelihood, is a function of this lambda parameter, okay, which is greater than 0. And the likelihood is therefore going to be a function of a product of a bunch of these different lambdas that are specific to each individual. And if we rewrite the lambda as exponential of beta 0 plus beta 1 plus the linear combination, that's how the regression parameters get into the likelihood function that we then try to maximize. That's the idea. Okay. Now, a related type of model for counts that we'll also talk about is the negative binomial regression model. Okay, and that looks very similar to the Poisson regression model, but the negative binomial distribution is defined by one additional parameter, okay, a scale parameter that lets us know how the variance changes relative to what would be expected for a Poisson distribution. Okay, so notice we're writing down y if it follows a negative binomial distribution. It has what's called a location parameter or a mean parameter defined by T times that rate parameter lambda. But then it has this additional parameter alpha that defines the scale of the distribution. Okay, and you can see down a little bit farther on the slide. The negative binomial assumes that the variance of that count is not just T times lambda, but it's T times lambda multiplied by 1 plus alpha. Okay, so there's an additional scale parameter that defines the variance, allows the variance to be larger than the mean in the case of a negative binomial, all right? And that's exactly what we saw for the count variable in the HRS data, okay? We saw a variable that we hadn't yet conditioned on any covariates, but we saw a variable where the variance was much larger than the mean. So that would suggest that this alpha parameter governing the negative binomial distribution is non-zero. If you look at the formula for the variance down at the bottom, okay? So when we estimate a negative binomial regression model, we also get an estimate of this alpha parameter, this scale or this dispersion parameter, and we can test whether or not that parameter is greater than 0 as a part of that analysis. If it is greater than 0, then we have support for the negative binomial distribution being a better fit. If it's not greater than 0, then we can simplify to the Poisson regression model before we make our inference for this kind of count distribution. The actual setup of the negative binomial regression model is very similar. Okay, the actual regression model in terms of the linear combination, the regression function, is the natural log again of that rate parameter lambda. okay, which is assumed to be greater than 0 in this case. And we write down the mean in the exact same way, right? Everything is defined the same way. We have the same offset variable. Mean looks the same as it did for Poisson regression, nothing different. What changes is the variance, which is defined by that mean parameter times 1 plus whatever the value of this alpha is. So now the negative binomial likelihood, and again, you can see what that density function looks like in applied survey data analysis. But that negative binomial likelihood is now going to incorporate the regression parameters through lambda, and it's going to incorporate that alpha parameter. So the maximum likelihood estimation process, we seek maximum likelihood estimates of the betas that define lambda and the alpha. Okay, so there's one additional parameter that we're estimating here, and we can then make inference about that parameter as well to choose between these two distributions. Okay. So the negative binomial, again, would simplify to the Poisson model if alpha is equal to 0 in this particular case. All right? Agree with me on the difference here between Poisson and negative binomial regression? Just one additional parameter to estimate when we're actually maximizing the likelihood. And everything stays the same with regard to pseudo maximum likelihood estimation, right? We're raising each individual's contribution to their survey weight. We're forming an estimate of the population likelihood, and then we're maximizing that likelihood function to find the maximum likelihood estimates of the betas and the alpha in the case of the negative binomial. Yep.
So you said when you run a regression for a count variable, and then you compare the means, and then the variance and the mean, they're different.
They're related to each other. So when you fit that model using linear regression, the variance of the natural log of the rate is a function of the rate. So that means by definition, the higher the rate, the higher the variance. So the variance is not constant as a function of predictions on the dependent variable. So that instantly violates the assumption of ordinary least squares regression.
When you decide now whether you are going to run a Poisson,
yep.
That should be, that should guide you if the Poisson would be the right distribution model. That
yeah, you try a Poisson, you could try a negative binomial, you could try a binomial model. Like there's different approaches for counts, but these, the Poisson, the negative binomial, they tend to be better fits for rare events. And this general idea of comparing the AIC that we talked about across different models, as long as you're using the same cases, you can consider different distributions, right? So which model gives you a lower AIC among several competing distributions for that count? It gives you a sense of which model has a better fit. And you can look at model diagnostics too, right? How do the predictions based on a negative binomial model do a better job of lining up with the actual counts than in the case of a Poisson or than in the case of a binomial? You can still look at some basic diagnostics to get a sense of how far off you might be from what actually occurred. Yeah. But yeah, this in general, these tend to be good distributions for these counts of rare events. That's the main message here. The question is just how the variance should be handled in this particular case. Okay. All right, so back to Na's question from a couple minutes ago. Many times these distributions are defined by this spike of zeros, okay, where it seems like there's a bunch of people where this event just never occurred. And we're trying to model the rate at which the events occur, but if the events never occur, the rate is really not defined. And that's what we saw in the Poisson distribution, right? We assume that that rate parameter is greater than 0. Okay, so what do we do about this mass of zeros for the people for whom the event never occurred? Okay, because that's a characteristic of count data. There are going to be a lot of zeros. Okay, so a couple different ways to deal with this. First of all, the negative binomial model does permit this conditional variance that's greater than the conditional mean. That's one way of dealing with the added variance that might be included by having all these zeros in there. But again, not ideal, right? Because we're assuming that that rate is greater than 0 by definition. Okay? So often the data will suggest that there's an always 0 group, okay, people where this never occurs, like people who never fell, maybe because they're in better health, or whatever the case may be, they're living in a situation where falling is not possible. Like in the US, if we think about people who are ages 65 and above, in the US, we have many people who we call snowbirds. And what that means is that if they live up here in Michigan or in some of the colder climates, they have a summer residence or even a winter residence down in the southern states. Okay? Where they go, there aren't stairs, there aren't basements, and they can just stay in the warm weather. Okay, the risk of falling is significantly reduced. So those might be the kinds of people who are in this always zero group, okay, because they live in an environment where there's a very reduced risk of falling, or whatever the case may be. So the data may suggest this kind of partition between people who have a risk of falling, they're at risk of actually falling, rates greater than zero, versus the people who are always zeros. They're never going to fall. They're not put into that situation. Okay. Take, for example, driving. How many accidents have you been in? There may be people who just flat out don't have a license and they never drive a car. They ride a bike everywhere, right? Versus the people who are driving every day and they're putting themselves at risk of being in an accident. Those are the rate greater than zero people versus the people who are never going to have an accident occur because they don't drive a car. Right? That's the idea here. Okay? So what do we do with all these zeros? This is where the idea of zero inflated Poisson and negative binomial regression models come into play when you have these two distinct groups in the data set. And so these zero inflated versions of the models can handle this particular case. It's called a two-step model, or sometimes it's referred to as a hurdle model. Okay? You get over this initial hurdle of whether or not you're at risk of having this event occur. Part of your model defines whether or not you're going to be in group A or group B. Okay, it's actually a logistic regression model for that part of the overall process. And then conditional on being a predicted member of group B, you model the parameters of the Poisson or the negative binomial distribution. Okay? So in a sense, you're modeling out those zeros, and then you're looking at the estimates of the Poisson or negative binomial parameters for those individuals who were not zeros, right? That's the idea of these zero inflated models, right? So the nice thing about this is that there are now software procedures that make it very easy to fit these zero inflated models, which seem like they would be appropriate for the distribution we were just looking at, accounting for all of the complex sampling features. For a long time, this wasn't possible, but now it's possible to fit these two-step models that incorporate simultaneously a model for membership in one of the two groups, and then a model for the actual counts that were occurring. Okay? So this is a very convenient, and it often applies to these cases of excess zero types of counts, where we want to model out that probability of having a count, of having a zero count. So we'll come back to that in a second here. All right, so whether you're talking about regular Poisson, regular negative binomial, or excess zero modeling, zero inflated models of the Poisson or negative binomial, it's the same estimation story. Okay? We write down the likelihood of conditionally having a non-zero count, which is going to be a function of logistic regression model parameters, and then the parameters defining the Poisson. That's each individual's contribution, okay, multiplied by each other. Or in the case of basic Poisson or negative binomial, whatever the density is for the Poisson or negative binomial, we write that weighted version of the likelihood function. Each individual's contribution is raised to the power of their final survey weight. Okay, that defines the weighted pseudo maximum likelihood estimation. And then we calculate the maximum likelihood estimates based on that weighted likelihood function. Okay, so no different from the other approaches we've talked about. The functional form of each individual's contribution to the likelihood just looks different, assuming these distributions, right? Then, using Binder's approach for calculating linearized variances, we can either apply that to the maximum likelihood estimates, just like we did for logistic regression, or we can use a replication method. So you can see, this is why Binder's early 1980s paper, he actually published it twice, but how many papers can you say? It was published twice in two different journals. That was the importance of it. That paper, 1981, 1983, dictates this general estimation and inference approach for so many different kinds of models. That's how important of a general solution it was. Forming the pseudo maximum likelihood method, finding a way to calculate linearized variances, we can apply the same general approach to all these different kinds of generalized linear models. It was just such an important advance in this particular area. And again, still Poisson, negative binomial, multinomial, ordinal, logistic, all these different models that we're talking about, they're using the same general estimation approach to get unbiased estimates of these regression parameters. Just such a crucial development that was evident in that paper. Okay? So nothing changes about the way that we go about estimating these models or the way that we estimate the variances. Okay, so interpreting the regression parameters, this is a little bit of a different story just because of the way the model is being defined. Okay, remember, we're looking at the expected value of the rate, or if we multiply each side of this equation here by the offset period, the expected value of the count as a function of those regression parameters. But let's just frame this as the expected value of the rate for now. So notice I'm taking t away from the right-hand side and just dividing the count by y in this setup here. So I'm looking at the expected value of the rate as a function of the regression parameters. We have an interpretation that's similar to what we saw with odds ratios in logistic regression. Okay? If we look at the expected value of the rate as the predictor variable x goes up by 1 unit, we have the expression that you see here, exponential of beta 0 plus beta 1 times x plus 1. If we look at the expected value of that rate when x is 1 unit less, we have the expression that you see here, beta 0 plus beta 1x. The ratio of those two expectations is going to simply be the exponential of the regression parameter for x, beta 1. Just like we talked about the ratio of the odds in the case of logistic regression. It's the same idea here. Okay? If we look at the ratio of those two expectations, the result is simply the exponential beta 1. What that means is that once we have a maximum likelihood estimate of beta 1 for our finite population, we can just exponentiate that beta 1 coefficient, and that gives us what's often called an incidence rate ratio, or an IRR. We're going to see that that's actually an option in Stata. That's how Stata declares the option for calculating these exponentiated coefficients. But that's a ratio of expected rates taking the offset variable into account explicitly. Okay? So again, if that offset variable is just a constant for everybody, we can think of it as being equal to 1, some constant observation period, then this just becomes a ratio of expected counts per observation period. Okay? But if that rate is different, or I'm sorry, if that observation period is different for different individuals, we're explicitly accounting for that here, looking at the rates. And this tells us how the rate changes in a multiplicative fashion as that predictor variable increases by 1 unit. So the interpretation is the same as we were making in logistic regression. We just have to talk about what's happening to the expected rate as opposed to what's happening to the expected odds, which is what we were modeling in the case of logistic regression. Here, we're modeling the rate. Okay, that's the only difference. So again, some people refer to this as the relative rate at which the event occurs. Some people refer to this as an incidence rate ratio, but either way, we get a convenient solution for what happens to the expected rate as the predictor changes by 1 on this multiplicative scale. So interpreted very much the same way that we interpreted odds ratios. Okay, and if we want to calculate a confidence interval for rate ratios, we do this again in a similar fashion to what we did with odds ratios. We just exponentiate the limits of the confidence interval for the actual beta coefficient. Okay, so we exponentiate beta minus the critical t-value times the standard error, and then we exponentiate beta plus the critical t-value times the standard error. That gives us a 95% confidence interval for the actual rate ratio. Okay, nothing different from what we did for odds ratios. The key difference, the key in terms of this class is that these are weighted finite population estimates of the regression coefficients based on the weighted likelihood. And these are linearized or replicate variance estimates of those weighted regression coefficients. Okay, so again, same approach. What differs is that we're inputting weighted estimates and linearized estimates of the standard errors to form the 95% confidence intervals. Okay, make sure we're making statements about the population. All right, so nothing different compared to what we did for logistic regression there. All right, so what procedures implement these different modeling approaches for counts that we've been talking about? In Stata, we would have SVY Poisson. Okay, that's for the classic Poisson regression model without the zero inflation. Or we have SVY MB reg. Okay, so that would implement negative binomial regression where we think there's over dispersion relative to the mean. There's more variance. The variance is higher than the mean. Conditional on the covariance. Both of those allow for linearization or replication methods to account for the complex sampling features. What's really cool in Stata is that they also make ZIP and ZINB available for the complex sampling setting. So ZIP is zero inflated Poisson, that's SVY ZIP. ZINB is zero inflated negative binomial. And again, this is where an individual's contribution to the likelihood is multiplied by their probability of having a non-zero count, okay, which is defined by a logistic regression model. So more parameters to estimate, as we'll see, but Stata makes it possible to do that in the pseudo maximum likelihood estimation framework. Okay? So very cool in that regard for dealing with those zeros. In R, we again make use of the SVY GLM function. Now we change the family to quasi-Poisson with the log link. That's what would set up the Poisson regression model. Okay, so that's how we set up the Poisson regression model in the pseudo maximum likelihood estimation framework, where quasi again is allowing for decimal weights in the overall likelihood function. The drawback in R when using SVY GLM is that there are no zero inflated commands. So if you want to try that two-step model to model out the zeros, we don't have an option to do that, okay? And there's no immediate negative binomial option, but you can estimate an additional parameter that captures over dispersion. Okay, so you're not estimating the negative binomial model exactly, but you can allow for an over dispersed Poisson distribution, which is kind of like the next best thing. It just allows for that variance to be higher than the mean, okay? So you're a little bit more constrained within SVY GLM when you're dealing with these kinds of rare events, but you still have some options here. The very, very, very curious drawback, which I can't believe I'm still talking about this in 2024, is that there's no survey Poisson or survey negative binomial or anything like that in SAS. Very odd that among all the SAS regression procedures, there just hasn't been more thought dedicated to this over the years. We've been telling the same story for year after year after year now, kind of waiting for this to happen. One person in the Summer Institute is before COVID, I'd say about 6 years ago, they were so perturbed by this. And they said, why, like, if we're always using Binder's method, why not just program Poisson negative binomial? It's a head scratcher, right? They were so perturbed by this that they programmed a macro that would take kind of the standard Poisson and negative binomial estimation with a weight included, and then automatically implemented like a replication technique. So they wrote a macro, and then they published a SAS users group conference paper showing this macro. So if you were to Google and look up like how to fit Poisson and negative binomial models in SAS right now, you'll see a reference to a Sugi paper that a Summer Institute student wrote because they were so upset about this. And SAS still hasn't addressed it. I don't have an answer for it. Okay? But unfortunately, there's just not an option in SAS. So what we often tell SAS users to do is use IVEware, use that SAS module, which can take a standard SAS regression modeling procedure and use it in the replication framework, similar to what this student had done. Use that student's macro as another way to do this, or use R Stata. Those are really the options at this point. So it's a perennial head scratcher as to why there's nothing yet available in SAS. Okay, so we're going to apply these procedures to that dependent variable that we talked about within the HRS. But let me pause for a second before we get into the example. Any general conceptual questions about Poisson, count models, negative binomials, zero inflation, anything about that? General questions about these models?
I've got a general question that may or may not apply.
often in the literature in agricultural economics, I see double hurdle models. So they
Yep.
have the first category, if you by E, for example, have debt, period, because a lot of farms don't, and then they model it depending on if you have that. I mean, that's not a count, but would it, does a name for double hurdle only apply to that, or just a discipline specific, or how does that work?
No. That's just a different kind of hurdle model. You can apply hurdle models in many different contexts. Like the classic Heckman selection model in economics is a hurdle model. You're modeling like the probability of being employed or having wages. And then for those who are employed or who have wages, what are the predictors of your actual wage? That model, which won the Nobel Prize, is a hurdle model. So hurdle models are applied in many different places. This is just particularly relevant for these count types of measurements where there's basically these two groups in the data. People who never fall for whatever reason versus people who fall at least once, right? Where it's natural to apply that kind of model. This is basically the form of Heckman's selection model for falling, or whatever the event is that you're trying to measure in the survey. It's the exact same thing. It was just a very important idea at the time, and it's taken off in many different areas, but this is the exact same thing. The cool thing is that Stata has adapted it to the complex sampling framework, and Stata also makes survey Heckman models available. So you can fit the Heckman selection model in this design-based framework, but it's using the same technology that we're talking about here.
Okay, thank you.
Yep. Other conceptual questions? Okay, let's take a break, and then when we come back from the break, we'll go through this example and talk about the different estimates and interpretation and so forth from these different competing models for these counts. So I'll start back up at about 10 after. So let's take about a 10-minute break, and then I'll start up at about 10:10. Okay, thanks. Also, folks on Zoom, I see there's more people now. So if you could check in, we had a check-in earlier. If you could just make yourself known, that would be good if you haven't already checked in.
I'm here now. My name is Damaris Lopez Mercado.
Damaris, okay, thank you.
This is Sophia. I'm not sure whether you got my name earlier.
Sophia, yep, okay, thank you.
Maida.
Yeah, I got you already, Maida, yep. Anyone else I've missed who hasn't yet checked in? Okay, all right, thank you.
Yes, I will send the link, or you send the link. I will send it. Yes, also they are asking.
For me, I was going for the evening because
The evening.
Yeah. I don't like meeting, then I can't contribute anything. I know. I meet and I'm just there. If I ask you questions, I'm no clue.
Well, or it's too late, so we have to.
I know it's too late, so I'll be banking on you for asking. The name, we didn't meet.
I asked the other child
Is it
before, and it said,
okay, then it's just
it was confusing.
communication problem. But
Yeah,
it's
why
fine.
not?
That's
It's
different.
fine, a lot of things are. Number 6.
Yeah.
Always have to,
When it comes to emails, we have to be
always,
very careful.
something.
Just relax. Just realize you made. The way we're talking here, every writer types something.
I'm not contributing.
And then yeah, the same. On the outside.
So something has to be done.
That's, yeah.
Whatever.
But I think some emails, they screen already that in the grades.
Yeah. I don't like it.
That's a just for you already. Yeah.
All the edits.
We can put it in HTTP and see what how it goes.
I do that.
Cheat. That's from my brother.
How are you?
I'm good.
Are you then fine?
Yeah, I'm better. The leg is doing better. Serious, really. Yeah. Well, very well.
How?
Yeah. I'm with. But I realized that's not good. Should try to.
Yeah, I really did should be.
Yeah.
That's
Yeah.
why last week when I was like, ah.
Yeah.
That's
So-
because we have different talents.
Yeah. What I did, I saw that it was possible to adjust. And I tried to adjust just to the house.
Yeah.
And I showed, and just parts. I don't have the results, but it's very complex. So my race, I just are. She's okay. Because there are some categories that first from each group, you know. So she's adjusting to adjustment. I was thinking about it had some options about I was right. I will do this, but doing this is too many. I was but it's not. So
Yes, I know. Yes.
You exercises.
Methods. But you have to do it because otherwise I can't solve finals.
You see, just read it. You see that
the same way. Around blocks. So we have to develop program solution. That's all. Yeah. Yeah.
I can help in writing it, even the results writing, if the data table is.
Yeah.
But she wants us to approve.
Yeah, but I think that she's trying to sort of adjust the program. Tomorrow. And two people in the office. Because I'm going to be able to do that. Because I don't know, or I don't know.
Good. In the exercise, I upload the tool, but I have realized that I make some errors, some time errors. So I sent to you as an email.
Okay, thanks. Yeah, we'll check for it. Yeah, no problem.
Together. And if you're so
Afraid?
no, not just afraid, but I mean, we can
I know, because I don't even know which word she's using. It's pretty much she hasn't defined.
Yeah, she's trying, yeah, she's.
So that's why I cannot write.
I can't show, I can't show you. I can't say yes, I can show you the variables that are abstract. So you have like. What's variables and what? I don't know. But I don't know how to use the science. Because and I don't know how to it's with data. We have 200 references, but they were designed. They design and they don't say how it is. So I can show you. Yeah, I should.
And she confirmed.
Yeah.
Because last time I felt like you were all.
Yeah. She's not. For me, it's like something like that. Minus knows that and but she's now.
Okay, let's get started again. So any questions again before we jump back into our example here? Any questions about what we've been discussing thus far before we go over the example? And I should reiterate, in Friday's lab, we're going to go through exercises in multinomial, ordinal, and Poisson and negative binomial regression. So we'll see additional examples in both state and R fitting all these models in Friday's lab. So, okay, so we're revisiting the 2012 HRS data on number of falls in the past 2 years or 24 months. So our dependent variable is that number of falls. And again, it has all those zero counts. So you got to think about how to handle those. All right. The predictor variables are going to be sex, age, centered, arthritis, so whether or not they have arthritis, diabetes, whether or not they have diabetes, and then BMI, which is also centered. Okay, so these are all things that we think in theory should be predictors of the rate at which people who are age 65 and above fall in the HRS target population. Now, like I said, in these kinds of counts, we have two pieces of information that encode the dependent variable. So our offset variable is going to be equal to a constant for everybody, but this depends on how we want to interpret the rate, right? We could just set this to 1 and say, how many falls per 2-year period do you experience? We could set this to 24 and say, how many falls per month do you experience? Okay, the choice of that constant value is up to us, depending on how we want to interpret that rate. All right, so it's kind of like what Gladstone was saying earlier. We can set this offset to be whatever we want, depending on our interpretation, or we could rescale this however we wanted. In this analysis example, we're going to set it to 24 for everybody. So when we talk about the rates, we're going to talk about the rate per month. Okay, because 2 years is 24 months. Okay, everybody clear on that point? And again, in different surveys, it might be 24 for some people, 12 for some people, 6 for other people. We have the flexibility to allow that offset period to vary. Okay, so here's the state in our code to fit the Poisson and the negative binomial regression models. Okay, so in this particular case, remember, number of falls is the dependent variable, and we have a second variable in the data set that's equal to 24 for everybody. If we don't explicitly specify an offset variable to the software is going to assume that that offset period is 1 for everybody. So everybody's exposed to the same observation period. That count was added up over the course of 1 observation period. So if you don't specify an offset, the software is going to assume it's equal to 1 for everybody. All right, here we're explicitly specifying that offset variable that's equal to 24 for everybody because we want to make our interpretation in terms of months. All right, so first data command, we're using SVY subpop because we're unconditionally looking at the subpopulation of people who are age 65 and above in the HRS. The HRS includes people who are 50 and above. We want to focus this analysis on people who are 65 and above because those are the people who received this question in the HRS. Okay, so that's our unconditional subpopulation. Okay? The name of the Poisson modeling procedure is Poisson. Okay? After that, dependent variable comes first, number of falls in the past 24 months. Then we list all of our different predictors. So our predictors in this case include gender with a reference category of 2, age-centered, arthritis, diabetes, both of those are dummy variables, so you don't have to declare IDOT for those, and then BMI-centered. Okay, so remember, age and BMI are continuous. Okay, so we're not treating those like factors. Okay, we're also centering them at their means so that the intercept makes sense. And arthritis and diabetes are categorical, but they're simple binary variables, 1, 0. So we don't have to declare them as IDOT. We can just include them in the model as they are. All right. Now, if we want to consider the competing negative binomial regression model with that additional scale parameter, we can use the command nbreg. Everything else looks exactly the same. Like we talked about, we're modeling the rate using the same regression function. Everything is the same, with the exception of the estimation of that additional scale parameter that allows for the variance of the counts to be greater than mean. Okay. Questions about the stata commands here or the structure? So the key addition is that exposure option where you put in parentheses the name of the variable containing the observation period for each person. Okay, that's the only difference here. Oh, and I should also mention again, I'm adding that IRR option to exponentiate the coefficients to give me those estimated rate ratios, those incidence rate ratios. If I left out that IRR option, I would just get my regular maximum likelihood estimates of the coefficients. Okay, so then I'm talking about, right, I'm talking about a log rate, which again is not the easiest thing to interpret. So those rate ratios are more helpful. Okay, after the asterisks, this is the R code that you would use. So we create that design object to start with, create that unconditional subpopulation version of the design object using H65P. And then we fit the model using SVY GLM with family equal to quasi-Poisson with the log link, okay, to set up the Poisson regression model. And we use that unconditional subpopulation design object. The model formula looks the same as we saw within Stata. Okay, so that'll fit that Poisson regression model. And again, there's no immediate negative binomial distribution within R here. Okay, so that's how we would fit the regular forms of the Poisson and negative binomial regression models. Nothing really fancy, nothing special that we need to do. We're just using different command names in Stata. We're specifying the offset and using a different distribution within R here. Okay, so as a reminder, each model command in Stata, we have that IRR option and the exposure option to indicate the observation period. IRR is again going to exponentiate the estimated coefficients to give us estimates of those rate ratios, and exposure is going to set the offset period. In R, that offset period is fixed to 1 for each individual. So question, going back to the way we wrote the model, there's no exposure option within R and SVY GLM. How would we specify the offset variable within R as a part of the regression equation here? How do we do that? Suppose the offset variable changed for different individuals. How would we specify that here? Remember the transformation of the equation that we had? We go back a couple slides. Stata makes it easy because it sets up an option. Remember what we did to the model here? We're adding just as a constant term to that model, the natural log of that particular offset variable. So that's another way we can just add that constant piece to the model specification. And we're not going to get an estimated parameter for that particular coefficient. So if we didn't want to assume that there was a constant observation period of 1, we could simply make that addition to the error code. Okay, but as it is, that observation period is assumed to be fixed to 1 if I don't explicitly specify an offset for that 2-year period within the part. Okay, so here side by side are the estimated incident rate ratios for each of these different predictor variables based on those 2 different competing forms of the model. Okay, and first thing you look at is that even if there's evidence of additional variance relative to the mean associated with the negative binomial, our inferences are almost identical. It doesn't make a huge difference in terms of the inferences related to these predictors if we allow for that additional overdispersion. Yes, technically it might be a better fit for the observed data, but in terms of our point estimates and the corresponding confidence intervals, really doesn't make a big difference. Okay, so that's the first general observation. In the estimation of that negative binomial model in Stata, we get a weighted point estimate of that alpha parameter. And you can see in the footnote for the table that the point estimate of that alpha parameter is 3.8. Right? So remember, if that parameter was 0, we have evidence in support of the Poisson. Okay? As it is, the 95% confidence interval for that scale parameter is 3.5 in the lower limit, 4.2 in the upper limit. Clearly not 0. So even when conditioning on these predictors, there's evidence that the variance of the distribution, the variance of the expected values, much larger than the mean. Okay? So of the 2 competing models in this case, there's clear evidence to choose the negative binomial, but it's not going to make a huge difference in terms of our population estimates. Okay, that's the first kind of takeaway point here. And again, that alpha estimate and its confidence interval will be displayed as part of the Stata output. We'll see that on Friday when you fit the negative binomial model. Okay, so let's just look at the Poisson model for the sake of illustration here. We're seeing that the estimated rate ratio for being a male again, remember what we're modeling here is number of falls experienced in the past 2 years, or rate a rate per month, I should say, of falls experienced. If you are a male, that estimated monthly rate of falls is multiplied by 1.29. Remember, when we exponentiate that estimated coefficient, we're multiplying the expected value of that rate. And we're talking about a monthly rate because we had that offset equal to 24. So the expected monthly rate of falling is higher by a factor of 1.29 for males relative to females, adjusting for these other covariates. Or you could say that the expected monthly rate of falling is 29% higher for males relative to females. Same way we interpreted the odds ratios. Okay? You multiply the number by 1.29, you're increasing it by 29%. We're just not talking about the odds, we're talking about the expected rate at which these events are occurring, monthly rate. Okay? And if we look at that 95% confidence interval for the rate ratio, it clearly does not include 1. Okay, for the coefficients, we'd be looking for 0 as evidence of the null hypothesis. Remember, for these exponentiated versions, we're looking for 1 in that confidence interval, because a 1 would mean that the rate is not changing. Okay, remember, and we're talking about people who are age 65 and above, right? That's our subpopulations here, so that's important to remember. That's who we're referring to. What about age? It looks like for each additional year of age, for above and beyond 65, there's about a 1% increase in that expected monthly rate of falling. So it seems small, but it is significant. Okay, that 95% confidence interval, it's close to 1, but it doesn't yet include it. Okay, so it seems like age does matter somewhat as well, where the expected rate of falling does go up, not as much as for other covariates here, but it does go up as you get older, above and beyond 65, which makes sense. Having arthritis, this seems to be the biggest player of all these different predictors. So if you're 65 and above and you have arthritis, the expected rate of falling is multiplied by 2.09. Clearly that confidence interval does not include 1. Okay. What is the percentage increase in the expected monthly rate based on that estimate? 109%, right? So the expected monthly rate will go up by 109% if you have arthritis relative to not having arthritis. So that seems to be the biggest predictor in this case among this elderly population. Having diabetes also matters. Okay, much like being a male, if you have diabetes, your expected monthly rate goes up by about 28%, okay, relative to not having diabetes. Now, taking into account sex, age, arthritis, and diabetes, it seems like your BMI does not matter. Okay? So in this older population, your BMI does not seem to be relevant for how many falls you're expected to experience in a given month. You see the point estimate there is pretty much right at 1. Okay? So it doesn't seem like changes in BMI are relevant for this older population in terms of the rate at which you experience falls. Okay? So reasonable results. Again, these are population estimates. It gives us a sense of which of these are the most important predictors. So there's certainly some implications here for people who need care, people who need monitoring, depending on their health profiles. And we could always add other predictors as well, but it seems like this model is giving us a reasonable set of results. And like I was talking about earlier with George, based on these models, you can save predicted values of the counts and line them up against the actual observed values of the counts and see if you're getting a reasonable replication of those counts as a function of these predictive variables. Okay, and our inferences, we would make the same interpretations with the negative binomial model. Nothing changes about the way we interpret the estimated rate ratios. We're just allowing for more variability in the dependent variable than the Poisson distribution would allow for. Questions, comments about these estimates and their interpretation? Any questions about the interpretation here?
Professor,
yep.
I have a question related to Poisson and the negative binomial.
Yep.
Since the results is very similar to
yep.
each other. So, for example, if I would like to make a study like considering number of accidents,
right,
and it follows exponential distribution. So in this case, shall I use Poisson or negative? What about the assumptions that should
Of these two, I would pick the negative binomial to make my inferences just because of the estimate of that scale parameter. Yep. So between these two, I would choose the negative binomial, given that estimate of alpha.
And after making a negative binomial, I can say predicted and residual as you told us, and I can make the fitted and the diagnostics.
Right. So there's a different set of diagnostics that are generally considered for generalized linear models like these. So there's different flavors of residuals and so forth. But at a minimum, you can look at the predicted values and see if they're in alignment with the actual counts to see if the model is doing a good job of replicating the observed counts. There are general goodness of fit tests based on the similarities of those counts, but those haven't yet been adapted like we have for the goodness of fit for logistic regression. There's no like ESTAT GOF that we can use for these survey commands. There is a GOF that we can use for regular Poisson negative binomial, but again, that's a paper that just needs to be written. Is how are we going to adapt that to the case of complex samples? So you're not going to see an ESTAT GOF right after Poisson. Best to look at the consistency of the predicted values with the observed. Go ahead. So remember the alpha, go back here. So in the negative binomial model, the alpha is a parameter that describes this added variance relative to the Poisson. Okay? So the expected value of y under the Poisson, remember, is this guy, which was also equal to the variance, t times lambda. Okay? The variance of the y under the negative binomial distribution is 1 plus alpha multiplied by that value. So if alpha is equal to 0, we're back to the Poisson case.
Oh, that's why in our case it's 3 points.
It's 3.8.
So it should go to binomial.
Exactly. That's what I'm saying. So it's clear. So we're testing the null hypothesis that alpha is equal to 0 to make a decision here. And if we look at that 95% confidence interval for alpha, it's 3.5, 4.2. So there's no evidence in support of the Poisson, but I was just making the point that even if you made that mistake, your inferences would be very similar. So in answer to Israel's question, we would interpret the negative binomial results in this case, but we wouldn't be too far off if we made that mistake.
And then we're gonna see how we get alpha before the model.
Say again.
We can generate this alpha before doing the model in theta or R.
Yeah, we can find that estimate of alpha in Stata. Again, in R, there's no negative binomial command. So we're going to see on Friday in the Stata output, you actually see an estimate of alpha as part of the output, and it's 95% confidence. That helps you to make that decision.
So, Professor, I have a question.
Yeah, Newman, yep.
In both Poisson and negative binomial models, we have BMI that we didn't get any gain, like it's 1. And
Right.
here we in the confidence interval, we are looking 1. I mean, the 1 fall in the confidence interval. Can you please explain that why we are taking 1 instead of 0? I think
because Newman, these are rate ratios. These are not coefficients.
Okay.
Yeah, what we're showing here are the exponentiated versions of these of the estimated coefficients. So we're talking about rate ratios, and a rate ratio of 1 would correspond to the null hypothesis, but that predictor doesn't matter because that says the rate is the same when you increase x by 1 unit as opposed to looking at 1 unit less.
Okay, thank you.
That's why we want to, if 1 is included in the interval, we would fail to reject them all. Yep, question.
Looking just the results, I would conclude that the adjusted model both are 0 inflated.
Yes, so that we're not there yet. Yeah. This is just this is what we would see if we tossed the zeros into the mix, right? So we're analyzing everything here. And again, we're assuming that rate parameter is greater than 0 for everybody. Okay, so it's not an ideal fit in this case because we're including zeros in the analysis, right? So we're going to see, Gladstone, what happens when we take that 0 inflated approach. We haven't gotten there yet. Yep. Okay, yep, Isaac.
So in the negative phenomenon regression model, we are taking the time, the cancer, and so lambda is the rate, and alpha is the starting for the weight.
No, alpha is a scale parameter that defines the negative binomial distribution. So the mean of the negative binomial is defined by t times alpha, or t times lambda, excuse me. The variance, like we saw in the previous slide, is 1 plus alpha times t times lambda. So alpha defines the variability of that dependent variable. And so we're estimating that as part of the parameter defining that model. Okay, any other questions about the estimates here? Okay, so back to Glaston's question. We look at this and we say, well, you know, we got a lot of zeros, right? And technically, again, that rate parameter in the Poisson is greater than 0. So should we, you know, fit one of these hurdle models and model out the probability of having a 0 or having a non-zero value, and then look at the relationships of these predictors among individuals who have actually fallen? So if you've actually fallen, how do these predictors matter for what your expected monthly rate is going to be? And again, Stata makes it very convenient to fit these kinds of models using the zip and ZINB commands in the design-based framework. Okay? So that's what this syntax here is showing. I'm only showing the negative binomial because of the evidence that we just saw with alpha, where it seems like the variance is far greater than the mean for this particular dependent variable. All right. So what we're doing here is, you can see we're adding the inflate option to the ZINB command for zero inflated negative binomial. That inflate option in parentheses, we're including predictors of whether or not you're going to have a 0 value on that particular dependent variable. Okay, so it's like a logistic regression model for whether or not you're going to have non-zero versus 0 values. That's the binary outcome that we're modeling. And so in those parentheses, as part of that inflate command, you predict that kind of part 1 outcome of having non-zero versus 0 falls. Okay? And then we use that information to condition in the likelihood for those who have experienced falls, what then are the most important predictors of experience of the monthly rate. Okay? So the key addition to the zero inflated commands is the inflate option that comes after a comma, where you think of a separate scientific process. Okay? Of all the variables I'm considering, what are the most important predictors of being in those two groups? Okay? Those people who have experienced a fall, those people who have not. And that might be a different set of predictors from what actually predicts the monthly rate of falls for the people who have experienced falls. Okay? So there's really two scientific questions that we're tackling simultaneously with these zero inflated models. One is a logistic regression model for having any falls at all. The other is the actual negative binomial or Poisson model for people who have experienced falls. Okay, so we don't expect these results to look like what we just saw. This is a different approach to analyzing these data. All right, so you have to give some additional thought because we're estimating really two models simultaneously here and answering two different sets of questions. Okay, everything else in the command is the same, including the offset variable and the IRR option to get rate ratios. And we're changing the name of the command to be ZINB to get the zero inflated negative binomial version. Okay, any questions about that syntax?
Actually, I have a question.
Yeah, Sophia, yep.
I'm wondering, in practice, how would you choose the 3 variables here included in the inflate?
That's where your subject matter knowledge comes in, right? That's where, as a statistical consultant, you can say, beats me, right? That's what I'm saying. You're answering two different scientific questions. So you have to set them up as separate processes. What are the most important predictors of experiencing any falls in general, first of all? And then among those who have experienced a fall, what's going to actually affect your monthly rate? Okay, among those who are in that risk set, if you will, what's going to affect their monthly rate? So you have to think, in those two different processes, are there going to be the same relevant predictors? Or is there going to be a different set of predictors that might be relevant for that initial selection model, if you will? Okay, those people who have experienced any falls versus those people who have not. So you have to think, again, you're answering two different scientific questions. What is the set of predictors here that's relevant for experiencing any falls? And then what are the predictors that are relevant among the people who have experienced any falls? Okay, they're two different sets of questions.
can you run maybe some preliminary logistic regression?
Sure.
Just to check.
Yeah, you could fit, like to inform that inflate part of this whole process, you could just fit a bunch of binary logistic regression models outside of the zero inflated framework to a binary indicator of whether you fall or not, to inform this. Sure. Nothing to stop you from doing that. But the point I'm trying to make in response to Sophia's question, you don't just want that to be a fishing expedition. You want to start with some theory about what predicts among this older population who's going to be falling, right? You want to start with a reasonable set of predictors. Make sure you're not omitting anything important. And then you can carry that forward into the zero inflation command. That makes sense, Sophia?
Yeah, thank you very much.
Okay, other questions about the syntax? Yep. Yeah, so inflate is in the background. It's basically creating a binary indicator, one if you've had any falls, zero otherwise, and it's fitting a logit model as part of the likelihood. And then for those predicted to have a one in the likelihood, what are the predictors of non-zero falls? So it's only focusing on estimation for those who had non-zero falls. That's the contributions of people to the overall likelihood. The people who don't fall are only contributing a predicted probability of not falling to the likelihood.
So
Right. So this would be an example where in theory, you think that diabetes and BMI have nothing at all to do with falling in general. But when you focus on the people at risk of falling, then they matter. Right? So that's where you have to bring in your subject matter knowledge and say that is a theoretical justification for including those in the falling model, but not in the binary model. Yep. Okay, so let's see what happens. This is the zero inflated negative binomial model. I'm not showing the alpha parameter, but we're again assuming that that's greater than zero in this particular case. So in the part one logistic model for zero inflation, okay, take a look at what we find for whether or not you're falling or not. Okay, notice what's happening with males. Okay, there's a tremendous impact of just falling in general for males. Okay, I joked a little bit earlier, males in general aren't doing a good job of taking care of themselves. They're not falling, or they're falling at much higher rates than females, just in general, a ridiculously higher rate, right? So 4.5, what's the percentage increase in the odds? Remember, this is a logistic model. What's the percentage increase in the odds of falling at all? 353%, right? These males don't take care of themselves for their entire life. Then they get to be 65 and above, and they're falling all over the place. Okay? Pain in the butt, right? But what's interesting, look at what's happening with age and arthritis. Okay? Remember, we're modeling the probability of falling versus not falling. Okay? What is our interpretation of the odds of falling as age goes up by 1 year for falling in general, falling at all? Think carefully, Carrie. These are odds ratios, right? As age goes up by 1, the odds are multiplied by 0.91, which means they're reduced by 9%. Yeah, we're focusing on the part one model and see that 95% confidence interval for the odds ratio does not include 1. Okay, there's a negative relationship. So again, being at risk, if you're older, if you have arthritis, you're probably not moving around as much, right? Your risk is reduced because you're not moving around as much of falling in general. That's the first outcome that we're modeling, okay? Especially for those with arthritis, right? You're at reduced risk of falling in general, right? But then when we turn to the actual negative binomial model for the monthly rate, focusing on those who have fallen at all, look what happens to arthritis. Now it becomes a very important predictor, right? So for those who have experienced any falls, and you can think of them as being the people who are still moving around a lot at these advanced ages, if you also have arthritis, your expected monthly rate goes up by 75%. Okay? So you can think of that proxy for falling or not falling in the logistic model as being a proxy of movement or activity or something like that. And if you have arthritis, your activity is limited. Okay? But if you're still moving around a lot, despite the fact that you have arthritis, you're probably going to be at your monthly rate of falling is going to be higher if you have that condition. Okay? Same for diabetes. Okay, so we thought diabetes would matter for the monthly rate among the people who actually were falling. Okay? And sure enough, it does. It increases your rate, your monthly rate by about 31%. BMI still doesn't matter. Okay, we're again seeing that same general result related to BMI. It just doesn't seem like BMI matters for the monthly rate among those who have experienced falls. Okay, age no longer matters among those who have experienced falls. Okay, what the monthly rate at which you experience falls is now determined by arthritis and diabetes, and also again klutzy males. Okay. Yep, Preston.
Curiosity. This reflects real data.
Yep, this is real HRS data. Yep.
The great difference among male for the logistic model is because of behavior.
Because of
behavior.
Could be. I mean, you could hypothesize all kinds of things. Like it could be, using substances. It could be past injuries, right? You could think about all these other possible variables that might be responsible for that. But I'd be willing to wager that even if you adjusted for those other kinds of covariates in that model, males would still emerge, right? They don't live as long as females. Yeah. They put themselves at higher risk with their behaviors and their activities. And that's showing up here in the real data for this population, especially for that falling in general. It's pretty astonishing. Yep. But yeah, you could, like I think Jupiter was saying, you could look at logistic models outside of this process as much as you wanted to try to inform the zero inflation part. But this is how we effectively model out those zeros and then put our focus on the most important predictors among the people who have at least one fall. And that's what these are showing up as. Okay, yep, perfect.
The regression, we have 0 and 1.
Yep.
The model. So in regression, we are accounting those who fall and those who do not fall.
Right.
This one also, the regression we also accounting 0 and 1.
No, the logistic regression is for a 0, 1 variable. 0, you have not experienced any falls. 1, you have. Yes. That's the logistic. The negative binomial regression is for the count. That negative binomial regression model is for the count among those who have at least one fall. So remember, we just talked about Poisson negative binomial regression is for counts. So we're modeling the monthly rate of falls for people who have experienced at least one fall. That's what this 2-part model is doing. We're getting rid of those zeros as a part of the modeling process. Right? That's a negative binomial model, not a logistic model. And that this is what Sarah was saying on Zoom. There are all kinds of these 2-part models. Like the classical Heckman selection model, part 1 is, do you have a job or not? Part 2 is, how much do you make at your job, right? So part 2 is a linear regression for your wage. But the people who have no wage because they don't have a job are thrown out. Right? So now we're focusing on the people who have a non-zero count in that part 2 model. Got it? Yep. Okay, other questions about this interpretation? These are very cool models and they're used all over the place because they allow you to answer multiple scientific questions at the same time, and they give you a better model for the actual substantive outcome that you're interested in, getting rid of the zeros. Questions, comments? Okay, so very cool. We can do that in Stata, like fully adjusting for the complex sampling features. Okay, as I mentioned, in each of the negative binomial models, the 95% confidence interval for the alpha parameter did not include 0. Okay, so that's evidence against the Poisson distribution. So again, back to Isra's question, we'd probably choose the negative binomial in these applications. And it is important to compare your estimates and inferences across these alternative models, just to see how sensitive your results are to the assumptions that you're making about the overall models. And you could test for the importance of weights using the technique that we talked about, add the weight variable, add its interaction with the other predictors. You could do that in each of the 2 parts of this model if you wanted to. Okay, all the previous techniques that we've talked about still apply here. Okay, but these are very useful models for these kinds of counts. Okay. All right, so that's what I wanted to cover today in terms of Poisson and negative binomial regression. Again, in Friday's lab, we're going to see examples of multinomial, ordinal, and Poisson and negative binomial. So we'll see examples of how to execute all these kinds of models in Friday's lab that you can follow along with. But any general questions about the example here or about fitting or interpreting these models? Any general questions? One question here in the room, and then we'll go to Zoom. Yep. So
I need to know the key difference when we try to use this model versus the regression. Because also it is a numerical.
Yeah. So linear regression, Aaliyah, for these rare counts, you're going to be very hard pressed to satisfy that assumption of normality in the residuals, no matter what predictors you include. So you're going to have 2 problems most of the time. You're going to have non-constant variability in the residuals, and you're going to have a residual distribution that, despite your best efforts, looks like this. Remember, for linear regression, we're assuming that the residuals follow a normal distribution. And that's going to be very difficult to justify with rare counts. With
the difference is rare counts or
rare
counts.
Yeah, so it'll be easier to satisfy assumptions of normality if you have a very common count. Like if I was, for example, collecting the number of emails I received per day, right? That's a count, but it's going to be a normal distribution. Summer Institute, way out here at the end, right?
Yeah.
Most days, somewhere in the middle, right? That's a count, but it's a very common occurrence, right? Going to fall more in a normal distribution. Here's a count, very rare, follows a very different distribution. So you want to choose a distribution that makes more sense for the distribution in the data that you're actually seeing.
So we have to plot. So
You got to look at the data, right?
you have to plot the normal, the Q2 plot, for example.
The plot, look at the QQ plot, look at your residuals, visualize, visualize, visualize. And that's not just for this class, it's for any data analysis. You've got to look at the data. Yep, George, yep.
In most studies, health studies,
Yep.
so they mostly want these two methods.
For counts, yeah, for rare counts, like rare diseases or like I said, doctor's visits, miscellaneous health studies, where you're trying to model a rate. Yeah, the Poisson, the negative binomial are very popular because they make sense for these kinds of distributions. But a lot of people try to fit counts into a normal linear regression model. Usually the problem that you run into that we talked about is this non-constant variance when you're dealing with counts. And one thing that people often do is they take the square root transformation of a count to try to make that assumption plausible. But I personally, again, thinking about the interpretation of a rate, I just think these models make more sense. So you can talk about the rate, you allow for different offsets, easier to work with the estimates from these models. So, but if you can justify the assumptions of linear regression and all your diagnostics look okay and everything, that's fine. As long as you're happy with interpreting the results the way they are. So. Okay, other questions, comments? Yeah. Oh yeah, now you had a question, yep.
Yeah, so for this kind of research question, do we always run these models to decide which model we're gonna fit for our data?
Yeah, if it's not clear, like again, looking at this kind of plot, you'd think, normal is not gonna make much sense, but I could probably fit Poisson negative binomial. Definitely, you want to fit those two just to see if you have evidence of overdispersion. Like that's a first step. And then if you do, again, you can go with the negative binomial approach. Think about what to do with the zeros, right? If you have an excess number of zeros, should I model those out using the zero inflated model? Yeah, fitting these different models as alternatives is certainly a good way to go about it. You just have to appreciate where we are nowadays with these procedures, because I would not have been saying that in the 1970s and 1980s, where you'd take a week to fit this model, right? Nowadays, we can easily fit both models, make decisions about what makes better sense and so forth. We have the ability to do that. It just wasn't always the case. So yes, that's actually good practice, is to try to fit these different models, see which one makes the most sense, has the best fit, and then proceed with your inference based on that model.
Yeah, so with the zero inflated, is there any kind of cutoff of zero values for you to kind of fit in the zero inflated model, or?
The reason you wouldn't use a zero inflated model is if you went to these estimates and nothing mattered for your zero inflation. It's saying that it's basically an irrelevant part of the process, or it's a part of the process that you can't predict, given these different variables. Then you can just focus your Poisson or negative binomial model on the people who have one or more falls. But nothing matters. Nothing drives whether or not you've fallen or not fallen. That's going to be rare. But in that particular case, you just get rid of the zeros and say they're not part of my estimation.
Okay, I'm not sure if that explained my second question about having part one and part two, because I understand each part, but I'm not sure how doing logistic with zero inflation can affect my interpretation of the NB regression.
Yeah, no, this is, again, the key difference to recognize is that in the zero inflated models, the negative binomial regression is excluding the zero cases, okay? The interpretation there is restricted to people who have at least one fall, right? So it's entirely possible that you could find different estimates in that particular case when you throw out the zeros. The first negative binomial model that I was fitting was including the zero, okay? And as I said, given that we assume that rate is greater than zero, that doesn't seem to make the best sense for this particular type of outcome. So the question becomes, is there a separate process that dictates being non-zero versus zero? And is that important to model? In this example, it clearly was. Okay, we had big, strong predictors of whether or not you had non-zero falls versus zero falls. So I would want to interpret the negative binomial regression in this case, okay, where I'm focusing on what predicts your monthly rate of falls among the people who have fallen. All of this depends on how you want to handle those zeros, okay, because like you noted earlier, the zeros aren't part of the definition of that distribution. So we have to figure out how we want to handle them as part of the analysis.
So with the syntax of the inflate syntax, does it matter if we put in the diabetes and BMI with
no, yeah, it's, I mean, you're estimating more parameters, but it's possible to have overlap between those two equations, definitely. If you think from a theoretical perspective that they matter in both cases. Yep.
So it won't affect our estimates or our models at all when it comes to this research question?
You tailed off there, can you say again?
So it won't affect in terms of the number of predictors that we put in the inflate syntax?
No. You can have different predictors there. Ideally, for these kind of hurdle models, you want to identify unique predictors of the inflate. These are called, the name's escaping me right now. They have a special name though in this case, but you want to identify unique predictors that act to inform whether or not you're going to have a non-zero amount of falls that don't appear also in the substantive model. You're trying to do as much as you can to model out the 1 versus 0 case. So you want to think again in theory, what could impact having non-zero versus 0 falls, but it's okay to have overlap. You want the best possible model for each of the two parts of the processor.
So now I'm just thinking, should we put in all the predictors in the inflate at once, or should we do it one by one, at least step?
You have to do that initial investigation. I can't answer that question globally, right?
Okay.
You have to do that initial analysis, like again, like Jupiter was suggesting here, do separate logistic regression modeling outside of this framework to try to identify the best possible inflate model. Do separate negative binomial model outside of this framework to try to identify the best possible model for people with at least one fall, right? You can fit these two models outside of this general framework to make the best inference where you're conditioning on having a non-zero fall. You'd use this zero inflated model, but you can inform the models that you're using here by separate analyses outside of this zero inflated model.
Okay, thank you.
Okay, any other questions? Yep, Isaac. You speak up, please.
Side over here.
Yep.
Basically, everywhere, this side, we are,
right.
But if you go back to slide 18, running the non, the negative model without considering the zero position.
Right, we're just tossing the zeros as part of that dependent, we're including zeros as part of that dependent variable.
So what impact
Well, again, it's a different process, right? That's everything we've been talking about. We're including the zeros here as one general overall distribution. And those zeros could be having a huge impact on the relationships of these predictors, right? If we're trying to model the rate at which actual events are occurring, and we have all these zeros included in the model, that could easily throw off these relationships, right? So I can't, again, say globally what's going to happen every time when you account for the zeros here, but certainly the estimates of your relationships could be affected. There could be a very different process for individuals with at least one fall, as opposed to when we include the zeros. I'm not sure what you mean by 2.
Yeah, just we have the part of the item 1. So that's the process to
Yeah, this is what I was just saying to Anhat, like do separate analyses, have a 1-0 variable for whether or not you have any falls or not, separate logistic models outside of this process, separate models for people with at least one fall, and see how those models compare to when you throw in the zeros as part of that distribution, right? There you'll get a good sense of whether adding those zeros is really affecting the results. Yeah. There's nothing to prevent you from doing that to inform the overall model. Okay. Good questions. I'm glad people are thinking about this. So any other questions? Okay, so I will post the lab notes for Friday. And again, we'll see examples of how to do all this on Friday. And then again, Monday, the full drafts of your final project are going to be due. And we'll try to get you the logistic regression homework with comments by Monday at the latest. So, okay. All right. I think we're all set for today then. I will see everybody on Friday at 10 o'clock.